Hello everyone, this is a video on how to use Gearotic Spur, which will appear on your desktop if you install the latest version of Gearotic. This was written because I got sick of trying to design shaft clamps and bearing flanges into gears that I make in CAD programs. Basically, when I print a gear, I'd like it to have a way to attach it to the shaft, and this is an easier way to do that. This will be a quick video. If you're familiar with Gearotic, you're already familiar with almost every setting on the screen, but the way these things are displayed are a little bit different in this program, and there are 3 stages to designing a gear. So when you start the program up, what you see on the screen right now is stage 1. Here we can simulate the gears to look how our mesh is. And then the only settings that I think I need to point out to people here is backlash settings. In some programs, you will adjust the shaft distance in order to adjust your backlash. I don't like to do that because it creates too many complexities in designing a machine. So I like to put my backlash into the tooth width, and you will see a slider here for tooth width. And I find on my 3D printer that even if I leave it at 0.5 for tooth width, they mesh very nicely on the set shaft distance. However, for many people, the 3D printers will print gears a little bigger or a little smaller. In this case, I would suggest you move tooth width down to about 0.48 or so, and you can see that this leaves a gap between the gears. Don't be fooled by what looks like a large gap in your gears. If you actually zoom in on one of these gears, and you'll see down here at the bottom right-hand corner, I've got measurements in millimeters. And if we just look at the distance from the edge of this involute tooth to this involute tooth, you can see that it's only about 1/10 of a millimeter or 2/10 of a millimeter. So it's not a big gap, but it does allow for a good backlash adjustment. Everything else here is typical to Gearotic, from the pitch and modulus to the pressure angle and so on. The only thing that I should point out here is that you can select normal or helical teeth, as well as involute or cycloidal teeth type. Once you do that, you will see on the right-hand side of your screen all the statistics for the gear diameters and so on, and the center distance at the very end, in this case 36 millimeters, as we can see. When you're finished designing your gear outline, that's when we would go to stage 2. Hit the stage 2 button, and you'll see it takes a second here. I've got a fairly fast machine, and it takes 3 or 4 seconds to generate these outlines of spur gears. These spur gears are generated using signed distance functions, so they're quite different from the spur gears that Gearotic actually generates. Their STLs are a much tighter manifold. It's just a better meshing system for these gears. That's not real important. Even the old gears will print quite well, but for some of you, in some instances, it's better to have a nice closed manifold. These gears can also be made quite small. If you're using a resin printer, for example, you could print a gear which is 1 or 2 millimeters across. Not a problem most of us will ever have. So enough said on that. So on this screen here on stage 2 is where we decorate our gears. And when I say decoration, I mean things like bearing races, lock collars. Let's take a look, for example, at a bearing race. We have 2 gears here, a blue and a red. The blue gear is always this first part of your menu system. The red gear is always the second part. This is important to note because right now I'm on decorate front and the blue gear is on the left. And if I hit decorate back, you can see the gears swap position. The first part of the menu is still for the blue gear. That's worth taking note of. So let's turn on a bearing race as the most simple example. You can see I can set an outside diameter and a race depth. And if I hit regenerate, you can see this blue gear now has a bearing race in it. You sometimes will see aberrations in there. You can see there it looks like there's a shadow or aberration inside that bearing race. Don't worry about this. In order to keep regeneration times down, we're in fairly low resolution until the final stage of gear generation. So here we've pressed in a hole for a bearing of 6 millimeter OD, 3 millimeters deep. So pretty simple to figure that one out. We can add a flange to that in case you have a flanged bearing. I sometimes like to put flanged bearings onto my system just because I have a lot of them laying around. And if we regenerate, we can see that gear now has a flange. One thing about the menu system, you'll notice I can roll it around and so on, but if I point my mouse inside this menu, nothing will happen. The menu overrides the screen's ability to rotate and so on, so keep in mind that by hitting this arrow up on the top, you can shrink that away and inspect either one of the gears. So again, there's our bearing race and flange. Quite often the problem when you put a gear on the screen is you need something to lock it in place rather than something to give it a bearing. So I'm going to turn off the bearing and flange, and we'll go to a lock collar. And in fact, let's put the lock collar on the red gear so that we can see it a little bit easier, and we'll hit regenerate. All right, so there is a lock collar, and you can see it's got a hole in it for a grub screw. The grub screw hole is right here. You can set the diameter of it. And for a lot of us, that's enough. A grub screw will screw into a PLA gear with a fair amount of friction. You know, it may be enough for you. If it's not, and you still want to use a grub screw, we can decorate back and then put a lock collar on the back of the gear as well. And if we regenerate, now that gear has two flanges, or sorry, has two locking collars, and you can put two grub screws in it and you'll get a bit more clamp. This is not good enough for some types of gears. It's just not enough pressure. You may want a more complex clamp, and that you will get if you click clamp style. Once we go to clamp style, I recommend that you first set your bolt head diameter. You can see that the other settings change automatically when I select a bolt size. It gives you average measurements, which will kind of ensure that you get a good result, but you're going to have to float around with these a bit to match your situation. So I'm going to say that we're going to have a 4mm screw in this, for example, the bolt head itself, and I'm just going to regenerate without changing anything else. You can see the system has decided to give us a collar of using most of the gear. These are small gears, by the way, so you wouldn't have much room for spokes and so on in these gears anyway. But here's your clamp collar. We have a hole that the bolt will go into, and you can see there is a ledge here where the head of the bolt will bottom out. The shaft of the bolt will then go through this second release hole, and the third hole is for threading the bolt into. Double-clicking your mouse will always take you back to normal, by the way. So that is a clamp style. Since we're split right down the middle here, it doesn't take much power on this thread to actually clamp down with a great amount of force on a gear. And again, you can put one on the other side if you really want to get some strong clamping strength out of that. I'm going to turn off that clamp style just for the sake of speed here, because I want to get through this video fairly quickly, and it's easier to show you the next stage if we don't have a bunch of clamps in the way. So I'm going to go now to stage 3. Here in stage 3, you can see the teeth of the gear have disappeared. Again, this is a signed distance function program, and I don't want to take too much time in the generations of the gears and waste your time, so what I'm showing you here is just the spokes. There are two types of spokes. This is a stanchion type of spoke. You can increase your rim size in real time. You can increase your boss size. You can twirl your spokes to give them angular dimensions, and you can dish your spokes. And as you can see, when I dish inwards, we get a dished in shape on those. Now you'll notice the second gear has a larger hole in the middle, and this is because I left the clamp collar on that gear, so you can see there's less area for the spokes. In addition to stanchion spokes, we have just circular spokes. We can increase the number of spokes, dish the spokes, so now you can see they're kind of dished in a bit. We can twirl the spokes just to get a design. And when you're finished and you've set a number of spokes and you're happy with the rims and so on, that is when we would hit the integrate button. This will add the teeth to your gear and will also create a high resolution output. So any artifacts should be gone at this stage. And there's our completed gears. As you can see, the spokes have been added in. You may still see a couple aberrations. That's the nature of doing something as complex as a gear with a signed distance function. But I printed many of these and I found none of them to be a problem at this point. So that's generally how you do your gears. If you are integrated, you can see that we have a spoke only. That would tell us to go back to the speed, get rid of the teeth for speed's sake, so that we can do real-time changes to our spokes. Then hit integrate, bring back our gears again, and you can see it takes several seconds for everything to get integrated. And when that happens, you can see two buttons appear: export left side and export right side. This will allow you to put out your gears to your desktop or to any folder you wish for 3D printing. And that's it. That's all you can do with the program. Every time you run it, it starts off as a fresh run. It will not remember your settings at this point. This is a beta just to give you quick access to these types of gears. One last thing I'll show you is the quality of the mesh of these gears. For those of you who are into meshing, I thought I'd take a quick second to show you the quality of the meshes that are produced by Spur. You can see that the tessellations here are much finer than what Gearotic puts out. Again, it won't make a difference to most of you for your 3D printing, but these manifolds are much tighter and follow contours much better than the previous STLs. There are algorithms involved in signed distance function which allow us to reduce the size of the most significant aspects of the involutes so that they don't take up quite as much room. A gear will always be a substantial STL most of the time because you want the accuracy of the involute curves, and Gearotic Spur tries to do that as best it can. That's all that you need to see on the quality of the STLs. I just thought it was worth pointing out in this case. So that's it. That's all I've got for you today. I hope you enjoy the program. It's in beta, but it is already released, so it will install, and you'll find a desktop icon when you start up the newest version of Gearotic. Thanks a lot for listening.